everybody. So this is the first of the 5 sections I will be posting this week, which will be covered on your final exam. This first one is section 4.9, and it is about antiderivatives, which is basically all that's covered in Calc 2, including a couple other topics. So this is mostly an introduction. Effectively, an antiderivative is a derivative that's been undone, as the name implies. But you could also call it an integral. You'll hear that. We'll talk more about that later, but I just want to give you guys a couple examples as an introduction as to what the big idea is. So if we have f of x equaling x squared, then we know that df dx is equal to the derivative with respect to x of x squared, which is 2x. And so the antiderivative of 2x is x squared you could also say f of x is the antiderivative of 2x. So if we look here, it's basically saying this function, our x squared, if we took the derivative of that, got 2x, and then wanted to undo that derivative, we get back to x squared. So antiderivative just undoes that, just like multiplication undoes division and subtraction undoes addition. Another example is if g of x is equal to the cosine of x, we know that the derivative of g of x with respect to x is the derivative of the cosine of x with respect to x, and we know that's negative sine of x. So g of x, which is cosine of x, is the antiderivative of negative sine of x. Okay, but there's something I want you guys to note. If f of x is equal to x squared and g of x is equal to, say, x squared plus 2, we have f prime of x is equal to 2x and g prime of x is equal to 2x. So the question is x squared or x squared plus 2 the antiderivative of 2x, right? So above, we took what we got as a derivative and undid it. Well, we see here that if we have 2x as a derivative, we could undo it either way. We could have x squared or we could have x squared plus 2. And the answer is technically both are true. And we take care of this by writing the antiderivative of 2x is x squared plus c, where c is some arbitrary constant. Or not really arbitrary, but we'd need more information to figure out what it is. So that's just a placeholder, unless we have more information. Okay, so just like derivatives, integrals have a power rule. So if you guys remember, we started talking about derivatives by using a limit, and we evaluated limits to find derivatives, and then we were like, okay, that's great, but we actually have a rule for the derivative of all polynomials. That was our power rule, so we'll just rewrite that so you guys can remember. It's what we've been using all semester, so hopefully you remember it. It was the derivative of x to the alpha with respect to x is equal to alpha times x to the alpha minus 1. Remember, we just bring down the power and then decrease the power by 1. And that was our power rule. So I'm just going to write the rule really quickly. Okay, and this is cheat sheet information. And it is the power rule for integrals. Which, again, is the same as an antiderivative. And this has some interesting notation, but I will walk you guys through it. So you have this kind of curvy S-shaped symbol. It can also look like this. Some people draw it really curved. I don't like to do that. If we have some function, x to the beta, I'm going to write this out and then I'll kind of explain to you guys what's happening. So, well, I guess this is the integral symbol, but you also need this dx here. And so basically that's saying you're taking the integral with respect to dx, right? So if you remember from the derivative notation, we have dx, and this means take the derivative with respect to x. And so we need both of those pieces to have this make sense. Same thing with this. When we need the integral sign, we need the dx to let us know what we're integrating with respect to. So just note that this means the integral of x to the b with respect to dx, or I guess rather with respect to x. And this and dx, the integral sign and dx, always go together. Okay. So anyway, the power rule for integrals is the integral of x to some power beta dx is equal to, we're going to increase the power by 1, or so, yeah, increase the power by 1, so it's going to be x to the beta plus 1, and then divide by the new power. And then we have to add a c at the end to account for that constant that we talked about up here, and that's your antiderivative. So if we're going to write this rule out, it is increase the power by 1, divide by the new power, and then add an integration constant. Which is that plus c at the end. Okay, so we'll do some examples. Before we found that if we look up here, the antiderivative of 2x is x squared plus c, so let's see how that works with our new power rule. So if we take the integral of 2x with respect to x, then from our rule we said we leave the 2 out front. Technically what we're doing here is pulling the 2 out of the integral. So it's 2 times the integral of x with respect to dx, or with respect to x. So we have that 2 on the outside. And then we're going to have this power is currently 1 on the x. So we add 1 to that power and then divide by the new power and add a c. And that gives us 2 times x squared over 2 plus c. And then when we multiply this 2 in, we get these 2's cancel. So we get x squared plus 2c. But technically this is just another constant. So we actually get x squared plus c, which is what we said earlier was our antiderivative. So just like the power rule for derivatives, the derivative, if we remember, so I guess these are just some rules for the integral. If you remember from derivatives, the derivative with respect to x of 2 functions added together is just the derivative of the first function plus the derivative of the second function. And the same is true for the integral. That is, if we take the integral of f of x plus g of x with respect to x, it's just the integral, oh gosh, I'm gonna run out of room. That's equal to the integral of f of x with respect to x plus the integral of g of x with respect to x. Okay? And there are tables in your book at this point where they talk about the integrals of trig functions and the integral of e and what they want you to like memorize with respect to that, but I'm actually not going to make you guys memorize that. I will let you know prior to the final exam which one of those you guys need to know. Hopefully none of them. I don't think they're very important, and in Calc 2, if you continue on, you'll actually learn how to find those derivatives better, like more formally, and I just don't think it's worth your time right now since we don't actually have the tools. You just do your memorization, and I don't think that's helpful. So let's just do some more examples and then we'll end it for this video and I'll do a second part. So first of all, we have, let's take the integral of 4x cubed. I'm going to put parentheses in here. It's just cleaner that way. So we have 4x cubed plus 7 minus 2, oops, not what I meant to do, minus 2 times the square root of x dx. So first I'm going to rewrite that a little bit to make it easier. That's the same as the integral of 4x cubed plus 7 minus 2x to the 1/2. We've worked with square roots before, so we know that's just the same as 1/2 as a power. All right, let's use our power rule here and see what we get. So we need to increase, remember constants just stay out front, so we can just leave that. We have several things being added together, so we're just going to take the integral of each one individually and then bring it down, but I don't actually have to write out, like up in our rule, how we have it separated out into each integral. We can just directly take the integral of each part and add them together. So I'm going to have 4 times x to the 3 plus 1, because we're going to be increasing the power on our x by 1. And then we're going to divide by that new power, which is 3 plus 1. And then we have 7, and technically here, This is 7x to the 0, because x to the 0 is 1, and 7 times 1 is 7. So here, we are actually having to raise our power to be 0 plus 1, and then we're dividing by 0 plus 1, minus 2x. We'll keep this minus just because it's part of our constant 2. So that comes straight down here. And then here our power is 1/2. So we're going to be adding 1 to 1/2, and that's the same as adding 2/2. And then we'll be dividing by that same new power, 1/2 plus 2/2. Okay, so let's simplify a little bit. I know that this kind of looks messy with all my addition and my powers. I just want you guys to see where the things are coming from. So we're going to have 4 times x to the 4th divided by 4. This 4 on top was our original constant. This is our new power, and this is dividing by our new power. For the next term, we have 7 times x to the 0 plus 1 is 1, and then we're dividing by that new power 1. And for this one with the fractions, we have 2 times x, 1/2 plus 2/2 is 3/2, divided by that same new power, 3/2. Let's simplify a little bit better. So these 4's cancel, and we get x to the 4th here. 7 times x to the 1st divided by 1 is just 7x. And then here we're dividing by 3/2, which is the same as multiplying by the reciprocal, which is 2/3. So we have a minus 2 times 2/3, which is a minus 4/3 times x to the 3/2. And then we have to remember to put a plus c after all of these, because we need to add that integration constant. Okay, so that would be your antiderivative. Let me write this. Antiderivative. I did not spell that correctly. Just the same as the integral of 4x cubed plus 7 minus 2 times the square root of x. Okay? All right, let's go ahead and do another example. It's going to be pretty similar. I just want to kind of get you guys into the rhythm of doing an antiderivative rather than a derivative. So for our second example, we're going to take the integral of 4x to the 21st minus 5x to the negative 7 all over x cubed with respect to x. And so if we were taking the derivative of this function, we actually have the quotient rule, which helps us do that. But there is no product rule or quotient rule for integrals. So I'm actually going to write that in red. So we're going to have to use algebra to be able to use our normal power rule. So these two both have this common denominator of x to the 3rd. So we can separate this into the integral of 4x to the 21st over x to the 3rd minus 5x to the negative 7 over x to the 3rd dx. And the only reason we could do that is because this bottom didn't have a sum in it. If we had, say, x cubed plus 1, we couldn't do it like this. We couldn't we couldn't do just this piece and this piece together. It would have had to be x cubed plus 1 and x cubed plus 1 on both sides. Okay, so it's just important to note how algebra works. Okay, so we're going to simplify this before we even take the integral because it looks pretty gross right now. So if you guys remember from algebra, when we have x to some power in the numerator and x to some power in the denominator, it's just x to the power in the numerator minus the power in the denominator. So we have 4x to the 21 minus 3 minus 5x to the negative 7 minus 3 dx. And that is the integral of 4x to the, can I do math, 18th minus 5x to the negative 10th dx. And now we can go ahead with our power rule. So we know we leave the 4. We increase the power on the x by 1, so we get 18 plus 1. Divide by our new power, which is 18 plus 1. Leave our negative 5 out front. Increase our power by 1, so we have negative 10 plus 1. Divide by our new power, which is negative 10 plus 1, and then add our integration constant. And then we just need to simplify. So we have 4x to the 19th divided by 19 minus 5x to the negative 9 over negative 9 plus c. You could technically end here, but it's nicer to clean up the second term a little bit. So 4x to the 19 over 19 is simplified as far as it can be. Here we have a negative and a negative, so that becomes a positive 5. And because we have a negative power on this x, it's actually in the denominator. So we have 5 over 9 times x to the 9th plus c. So that's your antiderivative or integral of our original function inside here for that one. Okay, so this is the end of this first video as an introduction to integrals / antiderivatives. Again, they're the same thing. And this is just like half of 4.9. I'll be continuing with the other one in the next video. Okay.